welcome to the Rust Live webinar. So this is part of the live series webinars that we host here at Amicus. My name's Christy O'Brien, and if you haven't heard of us, Amicus, as a recruitment company before, we specialise in recruiting for 5 key areas of programming languages. That's JavaScript, Python, Golang, machine learning, and Rust. And today we are joined by software engineer Maxwell Flitton, who will be giving us a talk on asynchronous Rust and an introduction to that. So the session will last around 45 to 60 minutes with a Q&A at the end if you have any questions. So we will leave the questions till the end, and Maxwell can answer them if you do have any of them for him. So anyway, that's enough from me. Maxwell, thanks for joining us. Please feel free to introduce yourself and also start whenever you're ready.
All right, yeah, thank you. So I just sometimes will look to my right because that's where the upcoming things are coming in. So yeah, this is a talk about an introduction to Rust and or async Rust really, and we're going to cover some core concepts, but I'll just give you a little bit about me as well. So I'm the author of Rust and Web Programming, 1st and 2nd edition, so working hopefully on a 3rd edition. I always, whenever I write a book, when I look back at it within 2 months, there's always more stuff you like to add, and also speed up your Python with Rust. So how to build modules like Python modules in Rust, so you can pip install them and then import them into your Python system and run them just like you would. So just like you would Python, which is quite exciting. And I've started writing the Async Rust book for O'Reilly with Caroline Morton. So been getting quite into async in this sense. So I also have to put a disclaimer, as always, with async, it's quite a complex topic. So there's always people who know more. So this is going to be like an introduction. It's going to cover the whole concept of async, but I don't claim to know the ins and outs of something like Tokyo and how they actually code the individual schedulers or something like that. So there will be some low level stuff that I'm just going to have to shrug my shoulders at. But I mean, we can see in the Q&A if anyone is, curious. So moving on, so we can say, like, what is asynchronous programming? And to be honest, I find this kind of like quite strange. The internet is always full of arguments on this sort of thing, or people have very strict diatribes about what async is. So I always think it's best to go through async's kind of like more a design pattern, and then you can use it for things as long as you know the concept of what async is, how it actually works, which is essentially just putting stuff on a queue and then processing it asynchronously and polling it. So if it's not being CPU used, then, we don't have to, we can just put it back on the queue and poll it. But you get these people say, do not use do not do computationally heavy stuff in async. It depends what you're using async for. You can use it for computationally heavy stuff, but we'll go back to that later on once we see actually what async is and how the mechanism works. So before we look into any sort of coding, this is kind of like you've got to kind of think about how you actually program and how you break down your problem. And we can have these things called tasks that are getting processed. We have these things called futures. Futures are kind of like things that are going to be computed in the async system, in the future. Task is kind of like a handle, or some people say tasks are in the queue. Some people say that tasks are handles. Again, when we go through it step by step, it'll just be clearer. And sometimes these statements kind of get used interchangeably. But this is kind of like the way that we break it down. So you only have 2 hands. So if you're in the kitchen, maybe you like to do this sort of thing, but most people, I assume, they'll put the kettle on, they'll do something else, and then when the kettle's finished, they'll do something else. So we've broken this down to like 3 possible tasks with 2 futures each. There is a bit of like dangerous assumption here in this, where we assume that it's going to take some sort of time to boil the kettle. So when the kettle is boiling, we'll we can insert the bread into the toaster, and then we can go and pour some milk in, in the mug and stuff like this. If the boil of the kettle is instant, then you'll be pouring, boiled water into the mug or something, or even if you haven't got the mug. So you've got to be a bit careful about how you actually structure them. And you can also see with this that the pour milk in the future and the instant coffee future, this is kind of computationally expensive. They're kind of blocking, as we'd say. So you may want to artificially put like a sleep in the prep mug task, so you cycle through all your tasks first and make sure that that stuff that's not CPU expensive, like boiling the kettle, that's something else that your hands aren't doing. You just have to wait on that, and the toasting of the bread kind of get started before you go back to pouring your milk. So these are kind of like tricks sometimes, and there is a specific word, but I've kind of forgotten what the word is. So first of all, we'll go through what the cycle is for async. You have a main, we have a main thread, and then we define that future. So, and again, that's not being computed right now. It's kind of like an IOU. It's kind of like this will happen in the future. And you can move this future around in your main, and it won't do anything until you actually execute it. And then when we do execute it, we spawn a task, and we have a scheduler closure combined, and we'll look at what that looks like in the code. And from that, we get a task, which in this sense, in this branch, we'll say is kind of like a handle. And then in the main, when we block the main to wait for that future to be computed, we'll pass the task into the block on, and we'll wait for that. On the other side, we also get a runnable out of this spawning of a task. We put this runnable on a queue. This queue then gets consumed by a thread that's looping, and it's kind of just taking stuff off that queue, and it's doing some computational process. It will sometimes, like, it may have to do something that's CPU intensive, or it may just see if something's there, kind of like has some information come back from a WebSocket in a HTTP request, or is that lock available, for a file or something like that, or a mutex. It's gonna poll it to see if that's sort of there. If it's not there, it's going to be pending, and it's going to put it back on that queue, and then it's going to get processed again. If it is actually the future is ready and it's finished, then you pull back, you say the future is ready, it goes back to the block on, and then we get a result, and we can do something with that result. So we'll start to look at that here with just a very simple example. I always just use sleeps in examples because they're just very straightforward. You don't have to think too much about that. You just think more about what the process is. So here's some dependencies, and this is what we're going to import, just all in a main file. You've got the async task, futures light, one cell, and flume. And the async task is part of the small kind of like collection. And I think I can post some things later on, or we can talk, and I can post some links to these GitHubs, and they're kind of like these very small repositories where you can kind of play about, and it's kind of like you plug in just exactly what you need. And you can see here that we've got in the main, we're importing like the future traits. We've got the catch unwind, which is kind of like you run code, but if it panics, it'll catch it, because you can't always guarantee what's going into the async runtime is going to be, you're going to match, every single outcome, or you're not going to directly unwrap it. We're going to be pinning something, which means that we're not going to be moving. We're going to ensure that, let's say, the struct that's been pinned is not going to move in memory. We've got the context in the poll, and this is what we're going to look at in the futures. Duration just for sleeping. We've got our async task, which is our runnable on our task, which is what we talked about. And then the futures and the lazy evaluation, because we want to like create the queue once, and then we don't want to create it again, because that, it'd be very strange. You just want to be sending it to that one queue for this example. So there's a lot going on in this slide, but this is actually how we would build a spawn task, right, function. So we can see at the top left, we accept a future, and has to implement the future trait, and it also has to have the send trait because we're going to be sending it over a thread. And it's also got a static lifetime. And this is because you may not actually block your main for this to come to fruition. And you have the right when you send a task to never actually wait for it if you don't want to. So it has to kind of like, your task has to be able to survive the whole lifetime of the actual program. And then we also have a task that also has the send trait, because you have to send it back from that thread, and it also has a static lifetime. And this is all just one. This is the spawn task function. I've just kind of broken it down. So in the next section here in the spawn task function, once we've accepted our future, you can see that we actually just we create our queue, and our queue has that lazy evaluation because we want it once, and it's a channel essentially that accepts a runnable. And Flume channels, you can just keep chucking things in, and they'll stack up. So they act like queues. It's quite good. And you have a sender and receiver, and then we have that thread, which is we spawn it, and you can see we've got that while, and we do receive from the queue, and that's our loop. It's going to be accepting stuff, and then we're going to do a catch and wind, and we're going to run our runnable, and then we return the sender. So we know from this that we can actually send stuff to the queue. And you can actually see when we go further down to the schedule, you can see it implements a callable for a runnable, and it's essentially a closure, but with that FN, it could be a function if you wanted. And we essentially accept a runnable and we send it to the queue, right? And we directly unwrap it. And then once we sent it to the queue, we actually get our runnable and we get our task. So this is where you get the async task spawn. This is directly from, one of our crates that we're using. And this is one of those things where I get interested, I read the code, and then I forget how it actually works under the hood, because it's just something you don't really use. You learn enough async to actually use it, and then you start going off and using it essentially. So from this async task spawn, we know that we get the future back, and we get the schedule. So sorry, we pass in the schedule function, we pass in the future, we get the task and the runnable back. Sorry. Then we schedule the runnable, so that gets put onto the queue, and then we return the task. And remember that this spawn task has been called in the main, so we're getting the task back. And then we can use that task to block the main to wait for to wait for the result to happen. So if we wanted to build our own future, this is a really good example here. Well, it's a very simple example. It's really not the best example, but it's a simple one. And we just have a struct that has a count. And we're going to say, okay, we're just going to keep increasing the count every time you poll it, and we're going to sleep for a second, and then once we get to count 3, then we're going to say that it's ready. Now you could do other things, like you could try and get a mutex lock, and then if you fail you say okay, pending, or you could listen and say, is there anything in the is there any information in a WebSocket or in a channel or something like this? But for this to just run this example, we're just going to do the sleep. And we can also see that we take in the context, and the context has a waker. And if you don't pass that in, then it can't be like reanimated again, essentially, because when this future goes back onto the queue, it's not being executed. It's only being executed when it's being polled. So this is quite a powerful thing in a sense, where you can have one thread, and it can, with very low resource, be keeping track of like multiple futures, and multiple tasks, and just polling them as and when, and saying, are they ready to actually be executed? And then there's some more examples here. So we've got an async function, which acts like a future as well. It's a function, but it's It essentially works like a future. And we're just going to print the async. We're just going to print saying async function, and it's just going to sleep for a second as well. And this is to demonstrate like 2 ways of actually sending tasks into this queue. And this is just a simple macro where we pass in futures, we block. So we use the future create to actually block on the future, and then we just append it to a vector and return it. So we kind of make our own join, function for futures. And if we run that, we kind of get this. So this is our main. We define 2 futures, and they don't do anything. Actually, on the right, this is the printout. If you actually ran this, they would start running, and we can prove this. So we spawn our tasks, then we spawn another task, which is an async block, and we're doing a wait with async function that we defined 4 times. Then we sleep for 5 seconds, and then we print before block. And you can see that this before block, before we start joining, is actually quite a way down. So as soon as you spawn these tasks, they start getting executed, which kind of makes sense, right? It would be a lot of extra hassle, no real benefit if we had some extra mechanism that would wait until you started to join. Started to block your main on the thing to actually process this. These are just going to keep getting processed in the queue. You're only blocking your main to check to see if that task you sent to the queue is actually finished, right? So it's quite powerful in this sense. But there is like a few things that we can actually see with this. The sleeping is blocking, right? Because if we go back, we're only doing a sleep with our async function, but you can see that they kind of all block together. If it was like that polling mechanism, like we've seen with the others, you wouldn't get that async function block all in one go. It would be jumping back and forth, just like the other futures that we made, the ones where it's got polling result 1, polling result 1, polling result 2, polling result 2, right? So we can see that sleep is actually completely blocking. But the other ones we got polled, when they get polled, they get put back on the thing, they get put back on the queue, and then the other one gets put back on the queue, and then this task 3 just gets hit, and it just consumes that worker until it's all finished. So there's something really going on here, and it's because our sleep function is not actually really associated with our runtime. And this is where it gets quite fancy. And this is when I'm going to say, like, I'll show you how laborious this sort of stuff is, and why you should really just jump to a well-established one like Tokyo if you're just exploring async, unless you're doing something very specific. So if we were going to do our async runtime, we were going to connect something like HTTP, or we're going to make HTTP actually async with our runtime, we would have to do all sorts of things. We'd have to actually define the stream. You can see here that we're actually making, we're fusing the service. So we're implementing the service trait for Hyper with our custom connector, which is something else, which is just, a struct here. Then we're implementing the async reads, the Tokyo async reads, and we're doing a poll read. And this isn't to go in depth on how we do HTTP. It's just to show you like the extra work you have to do if you build your own async runtime. So what we've just gone through, whilst it's quite educational, and you could use it in production, you've got an uphill battle, right? So we've also got our async write with our custom stream, and we have to do the poll write, the poll flush, the poll shutdown. And this works for our async runtime, but it's just a lot for a HTTP request, right? And you're not going to stop there. Like if you're going to want your sleep to actually work with your async runtime and not block it, you'll have to do a lot of stuff for that as well. So yeah, it's exciting, but you've got to be warned if you're going to go down building your own async Rust. And you can see here that our async function, here we accept the request body, and then we have to build our own thing. And we also had to build a custom executor, which I didn't put in these slides, and our custom connector, and we have to then await. So we can do something that's much more simple. And that is like, we can do the Tokyo, and we do the features form, we use futures, and then this is our async function. And you can see that we use a Tokyo sleep instead. And if we do that now, this is pretty much the same, except we didn't implement our own future. You can see now that we just get it to do a print statement. So we just say for our async, we're going to say when we're starting, when we're finishing, and we're doing a message. So if we look at this now, we've got 1, 2, and 3. And if you look at the right, we've got starting 1, starting 2, starting 3, finishing 3, starting, you know what I mean? So what you've actually got in this sense is the sleep is no longer blocking. Tokyo, the developers at Tokyo have done some really smart things. They've done all the heavy lifting for you. And they say, okay, when there's this Tokyo sleep, we're going to chuck it back onto that queue to be processed. And then you can also see now the power of await. So we've got this async function, but when you get to the await, if it is truly async, really that's giving permission for the executor to chuck it back on the queue. And then then go back again. And then when the next await comes in, then you put it back in. And that's quite powerful. So when you think of something like web processing, like a server, you have those async functions, they're going on those queues and then being processed. And also that's why people were so excited with something like async database connections, because then whilst you're waiting for that database connection, your server can go and process something else. So that's why async is, everyone's loving async in terms of web programming, because it just makes your whole program just so much more performant in that sense, right? It's kind of mind-blowing in that. And you can also see that because we're not waiting for the block, you can see the dashed line at the bottom. We've got the print before the block, before we do the join, and we use Tokyo's join. It's right at the end. These are all sleeping just for 1 second, but it's obviously way quicker because we're not holding up the scheduler. We're not holding up the executor, sorry, whilst it's processing, while it's doing that sleep. It's going, oh, that's a Tokyo sleep. It's going to go back, and it's looking at another one and looking at another one. So that's quite powerful as well. It's a huge upgrade. And again, it's kind of like something that we stressed. If you say, I want to do my own async runtime, but then there are reasons why you would want to do your own async runtime, not just educational, if you're doing something very specific. And this is an example. So in the book, we're in chapter 4, we kind of cover how we actually do task stealing, and we have multiple queues. And you can have like as many queues as you want, right? Those Flume channels, we can just have a couple of them. One could be high priority, one could be low priority. You could have a couple of threads working, looping and waiting for stuff in the high priority, and just one working on the low priority. But then you can also do like task stealing. So you can say, okay, if there's nothing in that high priority queue, I'm going to go over and I'm going to start taking stuff from the low priority queue. And that just means that you've got to juggle both of those channel endpoints, and you just got to switch between them. So if you're doing stuff that's very specific, then this becomes quite powerful. I'm not 100%. I need to actually play with it more. Tokyo has an interface where you can configure the number of workers per queue and all this sort of stuff. And so they may have already done this as well. So it may even be even less of a reason why you implement your own async runtime. But also this really, once we've looked at this whole process and we look at the flexibility of what we can do with these queues, we start to realize something else. And that's those one-liners that you see on the internet where you say, don't use async for, computationally expensive things. It really depends. I can see why that one-liner is so perverse everywhere, because you can imagine if you're using your async queues to process incoming requests, and then you chuck in some very computationally expensive, long-running tasks, that could block your incoming requests. So I understand why people are very on edge about it. But if you don't matter in which order your tasks are being processed, and your queue is not going to be used for taking incoming requests, then you could use an async to run something in the background, because you can have multiple threads pulling from these queues. It's not going to be the end. It's not an anti-pattern. It's not going to destroy your program. In fact, it can be quite convenient depending on what problem you're solving. So oh, we just got, yeah, so we'll go on to the next thing. But if we do go back to something like, let's say, Tokyo, this is how they did it. I kind of just ripped it from their blog, and you can see that they have like multiple queues, they have multiple processes, and they also have task stealing. So again, you get a lot of really cool stuff out the box. And I think if we go back to our Tokyo example, you can see I forced the worker thread in the top left to only have one worker thread. By default, it has, I think, as many as the cores. So, you wouldn't, you would get very different results. You get much faster results because they would just be processing quite a lot of these in parallel. But obviously we're not, I wanted to replicate our one so you could see the difference in it. So, wow, I'm talking much faster than I thought I would talk, because we're ripping through it. I'm seeing the updated thing. Do we take questions as and when they come, or?
So you can, I did just see that popped up then. So if you want to go ahead and answer that question now, then feel free.
Yeah. Okay. So Daniel's asking, like, what are the ideal use cases for async Rust? So very obvious ideal ones is web programming, HTTP connections, socket connections, that sort of thing. So you can actually use them when there's something that's not very computationally expensive. It is a very ideal use case. But as I said before, depending on your system, you could also use them for long running tasks as well, because you are getting that different thread that's just kind of processing those tasks. And then someone else has said, Hugh, sorry, I know Hugh from SurrealDB, but I always struggle with your surname. Any tips for debugging in async workloads? This is something that's actually quite hard. And it's something that we're exploring for the book and that as well, in terms of like mocking unit tests. They only go so far, because you then got to test against like certain other things, because everything's running async. So now we've kind of got the basic thing underway, I would move on to one of my favorite kind of implementations. And this is actors. So people who don't know what actors are, this is, again, like some people, so it's like some people say it's not really async programming. If you look at the async book, Rust book online, they'll say actually async has advantage over actors. So, I find this terminology like quite confusing sometimes. People put arbitrary kind of fences around them. Async, so actors in general, they have kind of like, in this diagram, they're kind of running on their own threads, and they have like a mailbox, and then they have methods, and they have their own state, and then they send messages to each other. And what happens is that this is actually quite good in terms of data races and stuff. So if you have like one actor that's going to be like sending kind of like orders to buy stocks or something, it can receive a load of messages, but it'll process them in the way that they get the messages. So it kind of kills the concept of data races. They're also quite easy to conceptualize, and they're very safe in this sense. So we can see that once we have this, we can have something where like we want to keep track of how much we're doing, like how much we're ordering, and we can go through that in this one here. So this is like an order book actor, and we just don't want to invest over a certain amount. And we're using Tokyo here, and we have a handle message. So we get a message which is defined on the right hand side. It's like an order, a ticker, an amount, and who I'm going to respond to, which is like a one shot. So here we can see that we accept a message. We make sure that we haven't gone over our total amount that we've invested. If we are investing and we're failing it, we're going to send a 0 back. We're going to say to that other actor, if you receive a 0 back, then we didn't make the investment. Else, then it's going to increase its its total amount, total invested, because they have has its own state. I'm just printing this because in this example, it's just so you can see how it runs in, when you were doing it. And this is for some other, project. And then you respond a message saying like, okay, one, yes, we did. And then you have another one-shot channel, and we send a tracker message to the one that's going to execute the order, saying like, we're going to buy this. And you can see here they've got an async run, and you just like wait for messages to come, and you have that await. So you can have this kind of like running in its own thread in real time, or you can just it's async and await, right? So you can also have this just going on the queues and being processed by your executors and stuff like that. And I'm starting to wrap up this talk, and I've only been doing it for 30 minutes. I thought it would be 45, so we're definitely a lot time shorter. I wanted to come up to the end on like a different kind of flavor, because we've got like the multiprocessor, we've got the web stuff. That sort of stuff is very much done to death. And I'm obviously not trash talking anyone who does the web stuff online. It just means that if you just Google async Rust web server, there's loads of that, and it's good stuff, obviously. But I'm saying, you're going to be sport for choice when you go on that. So I'm going to go down a slightly different avenue here, and we're going to talk about like modeling. And this is something that could be potentially controversial. It's still very new. So this is kind of like another potentially emerging case with, let's say, actors and async. So we have this thing called agent-based modeling, and my current day job at Oasis, we kind of do a lot of like financial loss modeling, NASDAQ and all that sort of stuff use us. And we model like catastrophes, or we get models of catastrophe providers, for those models, and we calculate risk of financial loss over certain geographical areas. Well, the Bank of England and some insurers and stuff are starting to look into like agent-based modeling, and that's where you start to have these turns, these sequence of turns, and you start to like have these certain rules kind of baked in, and they kind of interact with each other, but they all kind of keep their own state. And the reason why this sort of stuff is kind of getting really exciting is that like we have this whole thing called with delays. So these diagrams are from the book like Thinking in Systems, and when you think about mathematics and physics, the reaction of forces is pretty instant. So that's why our mathematical models are pretty good. But if you actually have a delay in anything, you start to get these like crazy oscillations. So on the left, we have like very simple like system where you have to like order cars based on how many cars you sold. And on the right is a response to the inventory. And if you kind of react too quickly, then you overcompensate. You could just get a blip where somebody comes and buys excessive amount of cars, and then you're overcompensating. If you wait too long, then you're going to run out of stock. But you can see on the right, you kind of get these crazy oscillations. And then when you combine this with like multiple systems, like this is very simplistic compared to like, let's say, supply chains or market economics, you can get very chaotic systems. And this is why it's taken us like, I would say years actually to rebalance the supply chains after COVID. This sort of stuff is very complex. And what they've actually started to do now, but you can only see is 2 citations. So I do stress this is potentially could amount to nothing, and I'll explain why, is that people are starting to look at agent-based modeling. From agent-based modeling to actor-based. So you actually start to get these async systems kind of sending messages to each other. And on the right is like how they actually managed like financial shocks to banks when certain crashes happened and all this sort of stuff. But you can only see it's like 2 citations. I read around it. I love actors and async programming, so I'd love this to keep going. But there are some flaws here. And it's potentially like, if we get, we've seen like the async, how we got like slippage with the sleep and stuff like this. You could potentially get some sort of slippage. So the advantage that agent-based modeling has is that they're steps and they're very repeatable, whereas you could get some quirks in the async system that could potentially cause spurious chaos that you just wouldn't see. On the flip side, though, it could also be simulating real world chaos, because you do get data races in real life. People sometimes could just have a phone call a couple of minutes apart. So this is kind of like an area that I wish would progress, but you can see this is 2021 and 2 citations, and there's not really much more going on. So maybe other researchers are also finding that async real-time actors are too, crazy to actually have this. But this is kind of like the final quote that they came up with, and they essentially just said it was better than agent-based modeling. I'm daydreaming. I'm kind of wishing that's true, but that's sort of the other cool stuff you could potentially do with async. And I think that's it, right? So I'm up for, should we take some questions?
Yeah, if anybody's got any questions now, feel free to use the Q&A section. And we'll just give it a couple of minutes, but if there's no questions that come through, we will, we'll wrap it up. We'll just give it 30 seconds or so. Oh, there's some coming through now.
So it says, what have you learned about teaching async Rust? That's kind of like an ambiguous question in terms of what have I learned about Rust, or what have I learned about the concepts of teaching? I don't really. I guess I could do both. Teaching async, I always work out that I speak a lot faster than I plan. Kind of run through things. In terms of the async, it always gets more and more in depth. I guess it's like that with most programming. You can go as low level as you want, and you kind of have to make a decision on, do you want to use async to solve problems, or do you want to solve problems in async? I've definitely moved to I want to solve problems with async, not use async to solve problems. Hence, if someone asks me like the very specific underpinnings of how tasks are specifically spawned, I don't really know. Is there any other questions? Okay, so from Marco, is there a limit to the number of actors that can be implemented with async Rust? I guess not, because you can actually have a scaling. So if your computer is big enough, I guess if you put it on a server, you could have as many queues as you like, because they'll be sending messages to each other. So I think that would be, I don't think there's really a limit to that. But I guess the more tasks you have, the more potential slippage you could get, basically. So if you have like, for instance, if you just have one task, it's going to get put on that queue and then it's going to get processed pretty instantly. Whereas the more tasks you have, even if you have like a simulated delay, you could potentially have more and more of a slippage. So, but they still work as tasks, right? So, and then this is great information. Does your book cover all of these subjects? Yeah, so the book does cover like how to build your own async Rust runtime, how to have multiple queues, how to do task stealing, also how to actually implement HTTP and stuff in your own async Rust runtime, and then how to implement actors and that sort of stuff as well. And then, so do you have problems with async Rust, which in normal Rust wouldn't happen? I think personally, not too much myself, but I'm quite risk averse. I always try and write the dumbest code I possibly can and try and write it as straightforward as possible. Have the tasks as small as possible, but you can run into some classic things. So if you're async, let's say that we have this queue and you have 2 tasks, and cross-contaminating those tasks can sometimes be quite painful. So you could say like you're not using async to wait for a piece of data that, let's say, another task needs to update, but that task is also stuck in the queue, you can actually cause like gridlock and stuff like that as well. So you have to be careful about like where you're getting your data from. But again, I think if you keep the async on everything, even from attaining the data, it will just get put back in the queue, and then the other one will be processed as well. So I guess it's actually quite safe, which is quite a good thing, because a lot of like, well, no, web servers, the requests are quite atomic anyway. But yeah, I think you just have to be careful really where you're getting your data from, and if one task is relying on another task or something like that. So any tips on memory management? So like with the Arc, etc. I tend to find that memory management is quite yeah, like when you do mutex and that sort of thing, it has quite a bit of overhead. So one thing I'm starting to look into is just keeping stuff as isolated as possible. Obviously a fan of SurrealDB, but we'll talk about something like, let's say, Redis or Postgres. You can have like these kind of Rust extensions that you can kind of code in. So if you can like offload your logic kind of there, then that would help in terms of memory management as well for the like your Arc and your mutex. Tokyo have kind of like their own mutexes, which you can just use yourself. But I generally try and avoid them because they take quite a bit of overhead. But and you can actually block if you just have one queue. I guess your memory management is not going to be that intense, because you're only really going to be having one access that mutex at one time, whereas the more queues you have, the more penalty you're going to be getting with like mutexes and arcs and that sort of stuff. So sadly, there's always a trade-off with arcs and mutexes. I try and avoid them when I can, to be honest. I think that's some people are, and also as well, like I noticed a few people here, like you and stuff. Obviously, just feel free to shoot me some more messages if you can't think of anything right now. We can cover that.
Okay, well, unless another one comes through, like the next sort of 10 seconds, then I think we'll wrap it up there. But yeah, Maxwell, it's been great having you on Rust Live today, and I really appreciate you taking the time to do this webinar. So this webinar will be available early next week to view via our YouTube channel. And as soon as I get the link for the YouTube video, I'll be posting that on my LinkedIn. So keep your eyes peeled, guys. And be sure to follow the live series account on LinkedIn to keep up to date with the clipped content of this webinar and also other events that we've done. And yeah, if anybody wants to take part in any of these events in the future, then I'm happy to chat about that and whatever topics you'd like to discuss. But yeah, Maxwell, I don't know if you have anything else to say.
No, everyone's been a great audience, I guess. Very nice questions. Sorry if I rambled a bit. I tend to talk quicker than I plan in these presentations. But thanks for your patience.
Great. Well, yeah, I think we can end it there then.
Right. Awesome.
Okay. Right. See you later, guys.